Okay, I'm not going to spend much time doing this because you're going to get onto the move in a few more moments and do the research for yourself. All I'm going to do is just quickly go through some of the uses of spectra, and your job is to work out how the spectrum is used in this case. So the first thing is, all of these 7 things here are able to be determined simply by measuring the spectrum. And often it has to be not measured in a photographic sense, it's got to be measured in a radiation intensity sense, because it's the amount of each of the different frequencies that give us information. So here they are. It's composition, so what we already know that every element has a specific set of absorption or emission lines. Density, that's how compressed the gas is, or how non-compressed it is. Temperature, we already know how that is worked. We use Vine's law for that. Pressure is nearly the same as density. So pressure and density, I'm going to, in a few more moments, combining into one thing. Whether or not the star is moving towards us or away. Okay. Now, yesterday we know that galaxies are very heavily redshifted or blue shifted. Stars, because they're close by, are not much redshifted. But because we are so good at measuring the spectrum, we can actually measure even the most minute redshift or blue shift. So we can actually measure their speed, their velocities. Part of this is also all stars and all bodies, like the Earth, every planet, everything, is actually in spin and twisting and turning. So we can actually also measure how fast a star is spinning in space. And though it's not within the course, we can also determine things or just characteristics of the magnetic field of a star or of an object. And that's mostly by radio telescopy, whatever they say that. Okay. Rightio. Now, remember, you don't need to take any of this stuff down. You'll be going through in a few moments and taking all this information into your yellow books. You already know this, that we can classify all stars into these 7 categories. There are categories down here, down past the M, the W, and the U's and T stars and so on, S-class stars. They are not general categories. They're the actual ones that we use for most of the stars in the sky. There are some stars which do not fit these categories, and we have their special categories for them. And we know that each of these categories, the O, B, A, F, G, K, Ms, are divided into further subsets of, say for instance, A1 and so on. Spectral class O at the moment only has 6 divisions. It's 04, 05, 06, 07, 08, 09, that's it. Okay? We have not seen an 00, 0 I should say, or an 01 or an 02 or an 03 star yet. But then that could be out there. Okay? And, turning off the lights there, we can classify their spectra simply by looking at the spectrum. I can look at this star here and say, oh, that's an 05 star. Not simply because of its temperature, but by the characteristics of the actual lines, the thickness, the density, the positioning, and the way that they present. So if you're an astrophysicist and that your job is to classify stars, you should be able to quite simply look at the spectrum and go, I know exactly that's a K5. Okay. Just by looking at that. And the reason is, and you've seen this table before, haven't you? Right, it's the one I gave you before. So this is the spectral class going down here. This is the temperature, the colour, but the other features. Now you actually have to memorise these other features. So this part here, these first 4 columns are memorisable, if that's a word. Okay? O-class stars are characterised by really deep helium lines as well as the hydrogen. They all have hydrogen lines, but the reason why helium is present is that helium is ionized. Now, O-class stars are so hot, they knock the electrons off any atom. So any atom that you've got cannot have electrons orbiting it. So everything that is in it is ionized. It also breaks down bonds. So because if electrons can't orbit atoms, we can't have molecules. So everything is simply ions. And O-class stars are basically just huge big balls of hydrogen and helium with some trace of other ions. Because it's slightly cooler, some of the helium can form atoms. And so we have electrons actually orbiting helium. Now, the electrons orbiting helium, that spectrum, is different than the spectrum of ionized helium. Okay, that's how good humans are. We know whether or not electrons are actually orbiting or not. So the spectrum of that looks different than the spectrum of the helium. A-class star, you still have very deep hydrogen lines. You have lost, you now start seeing ionisation of metals. Now, metals are ionised in the top three, but these become very clear at this point here. And so therefore, all A-class stars show these characteristics. Are you getting my point? Okay. You can start looking at, now you don't have to even be able to recognise an ionised metal line. But if you're doing, your doctorate PhD in classification in astrophysics, then you would be able to say, oh yes, it's like picking up a penguin and going, oh, I know exactly where this penguin was born, on what island and what time of the year and type thing. If you're a biologist and you like penguins, you have no idea what a penguin popped into my head. Rightio. Very quickly going to the others. We start seeing other metals start to enter into our our spectrums as we go down. The first metal that becomes very obvious is calcium, for God's sake. I don't know really why calcium becomes very popular, but it becomes very obvious in the spectrum. We start seeing in the lower ones iron and bonds, carbon-hydrogen bonds, especially in the K, because when I say so cool, they're very hot stars. But in comparison to an O-class star where you can't have any molecular bonds, these bonds down here, these atoms down here can start bonding, and we get carbon-hydrogen bonds. That's, if you're doing chemistry, that's a hydrocarbon bond. And CN, that's the cyanide bond, which is known for a lot of organic chemistry. And finally in M, we start seeing ions, sorry, not ions, but we see molecules of atoms of metals. So things like titanium oxide. Now, titanium oxide normally only appears on the Earth, but it's cool enough in an M-class star to see these type of bonds becoming. Okay, so the point here is that by looking at these features, the dips and the whatever of the spectrum, you can tell me exactly what class star it is. Okay? And if you're really good, you can not just tell me it's an A-class star, but you can tell me it's an A5 and so on. Okay. Right, yeah. And so these are, the next few slides just tell you a little bit more about that table. And this is the level, all that you need to memorise, okay? So you just need to know these things. Now, you don't often memorise this stuff until you really need to learn it, but it might be worthwhile just coming up with some mnemonic to memorise these type of stuff. Okay? Right. So that's the first use of our spectrum is to classify its spectrum as a spectral class, what type of star it is. The second is temperature, and we already know how to do this. This is Wien's law. So all of this information is simply reminding you about Wien's law. And Wien's law, as you can see up here, is this one up here. And we simply draw the curve over top. I think it does this, doesn't it? Yep. curve over top, you find your lambda max, you apply it to your Vine's constant, and then you can classify it using a spectral class table. Okay.
In the exam, will they give us the temperature?
Yes. Well, they wouldn't even you wouldn't have to memorise too much. You just the whole point is they'll never ask you, okay, work out the temperature. They have to give you Vine's law, by the way. They're not allowed to give it without the law. And then they'll say calculate and then suggest what type class. And you would say probably an A, and you use that probably bit. Okay.
Would they give it to us in nanometers or wavelength?
They can give it in angstroms or nanometers. And that's it. So yeah, you have to be able to read this. So that's basically 400 nanometers. Okay, that's 500 nanometers. And remember, or 600 nanometers. Remember, you just put a decimal place there, and that becomes nanometers for angstroms. Okay. So we've done that. We know how that works. The patterns of peaks and troughs also can give us. Remember, Vine's law is not exactly accurate. It's accurate to a certain level of accuracy. However, by just simply, if you're a very good astrophysicist, you can look at the peaks and the troughs of the hydrogen lines, and they can actually give you a much more accurate version of the temperature. So the patterns of peaks and troughs can take Vine's value and make it more and more accurate. And humans, as I keep on saying, are the most ingenious people. We can now take not just Vine's curve, we can take the peaks and troughs and we can really refine the temperature of our stars. What type of temperature is it taking? What is it measuring? Right, it's a surface temperature. It's not measuring the temperature of the core. The core's temperature is worked out by other means. Okay, so this is the surface temperature. We can work out the core's temperature by taking the radius of the sphere and then extrapolating back into the centre. Okay. This is an error on this thing here. I wrote potassium over here. I meant to write calcium. And that's not, that K doesn't stand for potassium. That stands for the K line of hydrogen. So, those three are the hydrogen lines. But I meant to write calcium here. So I will correct this on this here. But anyway, what I was talking about is once you've used Vine's law to give a ballpark figure of the temperature, you can then modify your temperature by measuring the distances between these three peaks, for instance. And you can see that they shift ever so slightly for different spectrums. And it's ever so slightly, because remember, Vine's law is only accurate to about the nearest 100 degrees Kelvin. This makes it down to the nearest 10 or so degrees, which is quite accurate for a star. Moving on. Okay. The next one is how fast are the stars moving? And we know this is to do with red and blue shift. Okay. So a body spectrum is red shifted moving towards us, away from us, and blue shifted towards us. And the amount of shift can tell us the velocity. Okay. The formula for the amount of shift, this is a very, very general formula of Doppler's law. So that actually gives you the equation for the shift. You don't need to know it. You don't have to use it. All you need to know is this is the standard laboratory hydrogen line 4, 1, 2, 3, 4. And here is it after it's been shifted. You measure the difference of the shift, and you can then apply that law and work out its velocity. Each line will shift ever so slightly different. Okay, the ones at the red end shift more than the ones at the blue, if it's red shifted. And then what you'll do is you'll just average those values. Okay. Rightio, so we can do translational velocity. Translational meaning motion in space. So it's translating, it's moving in space. Are we okay with that translation? Okay. And there is an applet there you can click and use. Okay. Now, rotational velocity. This floored me when I was at uni. This is back, remember, I want to be back in the 1990s. No. Okay. Don't worry, when I went to university. But even back then, we could work out how fast stars were spinning. And it just floored me how we could do this. And what we do is we just simply there's a star. Now remember, that star is just a pinprick of light in space. And we take our telescope and we focus it on only one edge of that pinprick of light. Okay? And we take the spectrum of that edge. Then we focus it on the other side and we take the spectrum of light. And then we focus it right in the centre and we take the spectrum of light. And what we discover is we take it in the spectrum. What we find is we take the spectrum right in the centre. That's the standard spectrum for that star. Okay, whether it be moving away from or whatever, because it's right in the centre. But if you take it on one edge, notice this one here is blue shifted. So that means that this edge is moving towards you. This edge over here is red shifted, so that edge is moving away from you. So by measuring the speed of this one going towards you and the one going away, you can measure how fast the star is spinning. And then all you have to do is, you know that this is a sphere, or very close to being a sphere. We can work out its volume. We can work out its radius just by the telescope. We can then work out how fast it's spinning, how many days it will take to spin, and so on. Isn't that just brilliant? Yeah. It just requires us to be able to get an optical instrument so fine that we can only look at this edge. And then the same optical instrument to look at this edge. And we have them. We've built telescopes with so fine abilities to resolve stars that this is just possible. And it's just like common nature, you know. These days, humans don't even do the calculation. I had to do calculations of this when I was at uni. But these days, you just take a photo and the computer spins out and says, oh, it's rotating at 5 times a day or whatever. Okay? So it's so humdrum and so boring these days. So that's rotational velocity, all to do with what? The red and blue shifts again. Okay? The last thing that we can measure is its pressure and the density, the amount of push in of the star is undergoing. And the way that this is done is simply by looking at the absorption lines. Okay? The thickness of the absorption lines just tell you how pressurized the star is. If you've got a less dense star, then you have narrow spectral lines, very thin. If you've got big, fat, broad spectral lines, absorption lines or emission lines, you know that you get it's high density, which means it's really under pressure. Okay? So, the densest stars that we have are basically main sequence. Main sequence are small, the dwarf set of stars. Gravity's pulled them all in, and they're happily fusing hydrogen into helium, aren't they? But as they die, what do? They start to expand into one of the other classes, the brights and the super brights and so on. And as they expand, they become less dense because, remember, a star doesn't suddenly create new mass, it's just getting more volume. And density is mass per volume. If the volume gets bigger, the density must drop. So these, the bright supergiants and the supergiants, are very less dense. These would really float in space. Okay, they're very big stars. They've got massive mass, but they've got massive volumes. Therefore, very dense, very less dense, very not dense. How many ways can I say that? Main sequence stars are the densest of the stars. So we can tell the difference now between a main sequence star and a bright giant simply by its density. Because you know that at that top corner, the corner up here, that's the top left-hand corner of the of the Hertzsprung-Russell diagram, all the lines start to converge. And sometimes you can't work out if it's a main sequence or it's a superprime O and so on. We've got to be able to determine those. And so we simply measure its density. And the way to measure the density is simply, there's the luminosity classes. We all know those now. Okay. And you know where they appear on the Hertzsprung-Russell diagram. This is what I was talking about, that little section up there. We can't tell the difference just by its position on the Hertzsprung-Russell diagram, so we have to work out a way of getting its classes, its luminosity class. And this is what we get. The top one here has thin, you see it's quite thin black lines, absorption lines. The bottom one here is thicker. Okay? Now, which of these, that's an A3 class star, so it's an A class and it's a third class of A, so its temperature is approximately 10,000. Well done. Good. This is class 1, so there are two classes of luminosity, class 1, that's the bright, massive supergiants and the bright supergiants. This is class 5. What's the class 5? Main sequence. Now, notice the main sequence has broader lines. And the amount of broadening, and we call it pressure broadening, can tell us the luminosity class. Okay. So all you have to do is measure it, say, okay, now in a main sequence star, the broadening is approximately 5 wavelengths, 5 nanometers. In this one here, it might be only half a nanometer and so on. Okay? Got the idea of how it's done? Remember, your job is not to be able to do this, but know this is how it's done. Okay? So, pressure broadening, the more dense a star, the more these lines are thicker and blacker. Okay? So, are you okay with that? Moving on to the last thing that we can determine is composition. Composition is simply what the star is made of, and we know that most stars are made of 99 or so percent of what element? Hydrogen, and also a percentage of helium. Good. And then all the others are trace. But what are the traces, and can we actually work them out? And the way we do it, every element, every molecule, every compound has a specific set of absorption line combinations. And if you want to go online, you can actually get the entire library of every known human compound and say to them, okay, if it's, just say for instance it was hydrazine. If you had a sample of hydrazine, it would have absorption line in the following frequencies, blah, 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 blah. Okay? Now, in the old days, humans used to try and work that out themselves. These days, a computer just suddenly goes, hydrazine. Okay. Thank God for computers. Rightio. There's another app there for you to work out. Now, you've got to remember this part here. The strength of the lines is dependent on the temperature and the pressure. So the broadness and the darkness, the blackness of your absorption lines, has nothing to do with the amount of that element present. It's to do with pressure and temperature. So just because you've got nice big black hydrogen lines does not mean there's more hydrogen in the thing. Okay? It just probably means the hydrogen is more under pressure. It's more like to be a main sequence star. Okay? So just because the absorption lines are weak, it does not indicate the relative abundance of the element. Okay, does that understand what the word relative abundance means? Okay. Here are a few signatures. We've already seen these. We've seen the hydrogen. Hydrogen has 4 main lines, 1, 2, 3, 4, and then it has a group, what we call Lyman series, up the other end, nearly on the level of UV. These are the Balmer lines, by the way. That way you don't need to know these names. But if you see that pattern, you know hydrogen is present. If you see the famous 2 double lines of sodium, you know sodium is present, and so on. Neon, if you understand, this is where the neon signature is. Have a look at it. Neon is used for lights, and the neon lights are normally always either yellow, orange, or red. Reason? That's what they emit. Okay. Rightio, we've done that, we know all those. And moving on. Our sun, by the way, this is our spectrum of our sun. It's very normal spectrums you see like this are, all in one go. But in reality, the way that humans do it and the way computer programs do it, they have to stretch the spectrum out into really like meters of length. So here is a spectrum, a single spectrum of the sun, where that's the top strip. Then that joins onto this, and that joins onto that, and that joins onto that. So this spectrum would be about wide of 2 rooms. And that means how accurately we can measure these lines to the nearest nanometer, actually nearest angstrom, which means a decimal. This is a blood sample. This is not one taken from a star. This is from a mass spectrometer. A blood sample has been placed into a mass spectrometer and it's been created into a spectrum. And this person is dying from heavy metal poisoning. So they have to work out why this person is dying, and this is the laboratory result. It's only a snapshot. The actual spectrum goes from probably the end of the lab to the end of the other lab. But it's this nice little section in the centre that I just took a shot of, and you can see how much chromium is present in this person's blood, which is not 2, it's chromium 2 that they're dying of, by the way, I think. Okay. This person worked at a smelting factory, according to the... Okay. This is the exercise that's in your book, and you have to work out, obviously, it's an exercise that comes from a trial paper. This is the star's object, okay, and you have to work out, given these, what elements are present. Okay, so you can have a go at doing that as well. Okay.